beta, alpha, beta, alpha, beta. Okay, and I'm going to call this I, and all this J. I'm going to call this I, and all this J. I'm going to call this I, and I'm going to call this J. Okay, and then I'm going to sketch. Okay, I don't know where is it. I did not calculate. I'm going to sketch the centroid. I'm going to sketch the centroid. So I'm going to sketch the centroid. So this one, I'm guessing the centroid is here. The next one, I'm guessing the centroid is here. Okay, and the last one, the centroid is on the z-axis. Okay, so all the green are all our centroid. Okay, so remember, I told all of us to focus, okay, on the equation where stress x is equal. So for this case is mz over izz multiplied by y. Okay. So from the centroid, we call this y1, the distance from here, okay, to the extreme. So either alpha or beta, the y1 distance is the same. Okay. Then we're going to have y2. Okay, this is y2. Okay, so that is y2. So when it's y2, the distance is the same for I and j. Okay, so I'll write this out. So for point alpha and beta, right, the y is equal to y1, right? So for this case, in that sense, okay, stress x alpha, point alpha, is equal to mz over izz multiplied by y1, and this is equal to stress x beta. Okay, so therefore stress x beta or alpha is equal to stress x beta. Okay, right? Okay, Milika, I'm explaining it to you now. Okay, so now if you look at I, or all of you know, okay, mj, right, y is equal to y2, right? Therefore stress x I, which is equal to mz over izz y2, is equal to also to stress xj, because they share the same y distance, right? So therefore stress x I is equal to stress x at point j. Okay, right? So whether it's symmetry or not is dependent on the stress field. Okay, so whether, so another condition, okay, whether is symmetrical or unsymmetrical bending is dependent on the stress field distribution. Okay, so two conditions. Okay, two conditions. So you can see the first condition is, as mentioned earlier, the moment, the applied moment can be either my or mz. It cannot be both. Okay, it cannot be both. And then the next condition, okay, whether symmetrical or not is dependent on the stress field distribution. So for this case, right, all of them are under symmetrical bending. Why? Because stress x alpha is equal to stress x beta. Stress x in the x direction at point I is equal to point J, because they share the same what? They share the same y distance from the centroid. Okay, and the formula to apply is stress x mz over izz divided by y. So regardless of the point of interest, okay, regardless of point of interest, very bad English, okay, I'm writing as I go, okay, mz and izz are constant, right? It's only your y that's changing. Okay, it's only the y is changing. Okay, so this is how we identify symmetrical bending, and we have to get this clear. Listen, I did not know about this when probably until like 6 years ago. Okay, I had the same mindset. Whether symmetrical bending or unsymmetrical bending is dependent on what? The loading condition, i.e., if I had like the one on the left is symmetrical, the one on the right is unsymmetrical. No, nothing to do with that in terms of bending. It all depends on what? On the stress field. Okay? I mean, it has something to do with it, as in the applied moment has to be in the my or mz. Okay, or not n, or. Okay, so again, our circle or. Okay, and then if the load on the left hand side is equal to right hand side, they are known as symmetrical bending. Okay, so now this is one of it. Okay, now let's look at a condition of unsymmetrical bending. And I believe you guys have seen this before. It's just recapping. Okay, but I'm just making the definition. Why is it defined this way? Okay, so let's look at unsymmetrical bending now. Okay, let's look at anyone. Any questions so far? I hope this is clear. Yeah. If not clear, I will repeat again. Anyone, any question, please? Okay, I hear nothing. Right. The next one is we are going to look at unsymmetrical bending. So I'll write for you the formula first. Okay, so for unsymmetrical bending, the formula that we have to use is stress in the x direction is equal to my over iyy multiplied by z minus, okay, minus mz over izz multiplied by y. Okay, so this is the formula acting about, sorry, the formula for unsymmetrical bending. Okay, and by looking at the formula, the first definition of unsymmetrical bending is when bending moment is applied in both y and mz. Okay, so for this case, the difference is the moment is applied in both. Okay, so now we are going to look at the cross-sectional view of a beam. Okay, or before we do cross-sectional, I'll do a 3D view. Okay, I try to sketch a 3D view. So in terms of a 3D view, yeah, so this is our beam. Yeah, so this is our beam. Okay, so the beam is cantilever. Okay, is inbuilt. Okay, and then we have our axis. So this will be our y. This direction will be our x, and then this direction over here will be our z. Okay. So now the applied moment is applying this way now. Okay. So I'm going to call that our m. Okay, the applied. So the applied moment, okay, based on the transformation that we see, it has component about the y-axis and it has the component about the z-axis. Okay, so now we are going to view the cross-sectional view. Okay, now we're going to view the cross-sectional view. And what you will usually see when the moment is like this, you apply the right hand rule, and the moment is acting this way, right? Oh, bad drawing. Come on, Eugene, wake up. Okay, so this is the rotation of the moment. Okay, that is the rotation of the moment. Right. So now we are going to look at the cross-section view now. We're going to look at the cross-sectional view now. So we have our cross-section view. So this is y, and this is z. Okay, and this is our rotation about x. Okay, so I'm going to sketch up our cross-section view. Okay, so this is our cross-sectional view, and I'm going to locate our centroid about the z-axis and the y-axis. Okay, so these are our centroid. Okay, so all these are centroid. So let's look at the moment, and then the moment over here. Okay, it's usually measured from x. So this is our theta. Okay, so I'm going to put the moment over here. Okay, so this moment, that is our theta, right? And this is our m, and this is the rotational direction based on right hand rule. Okay, so we know that we can break this down into two components. We are aware that we can break this down to two components. So we will have our, this will be our m z, and then the next one will be our my. Okay, the next one will be our my. And to write the formula for each of them is very straightforward. So we have mz, right? You have mz is equal to m cos theta, and then you have my is equal to m sine theta. Okay, so we are going to apply what I taught you. Okay, remember last week we talked about the moment vector, right? Let me help you recall regarding mz. Okay, so if we look at mz, the rotation of mz, okay, is in this direction. So that is our mz rotation, right? So for mz, over the head of the arrow over here, the mz is in what? Compression. Okay. The tail end is what? Tensile. Okay. I don't want you to depend on the formula. You forget the formula, you are game over. Okay. I did not understand this in 2P. Now I'm starting to understand. Milika, it's not you did not understand, okay? You had